This is lesson 12 in this series on fluid mechanics in medicine, and the topic is surface tension. The learning objective of this video is to understand the concept of surface tension and how pulmonary surfactant improves respiratory mechanics. Whether or not we realize it, we see examples of surface tension every day as it manifests in a wide array of common physical phenomena. One such example is how we can take a bowl, fill it with water, and float a piece of paper on top, despite the paper's density being greater than that of the liquid. Although this would seem to violate the principle of buoyancy, as discussed in lesson 2, it's something that everyone has observed at some point. Another example of surface tension is the tendency of water to form spherical drops instead of a continuous stream when flowing from a faucet at a relatively slow rate. The drops aren't perfectly spherical on Earth because of the effects of gravity and air resistance. However, water droplets in space, where these are not factors, do form perfect spheres. Here's another example. A small puddle of water on a flat horizontal surface. Although it would seem that water should collect in puddles, that's only because it conforms to our common experience, not because it makes intuitive physical sense based on most people's knowledge of physics. Suppose if all we knew about the puddle is that it is composed of countless individual molecules of H2O, and gravity is pulling each of those downward to the lowest possible level, and if water as a liquid freely flows based on the forces that are acting on it. If this was the extent of our knowledge of water, we would logically conclude that the puddle would continue to spread out in all directions until it had reached a depth of a single water molecule. That way, each individual molecule would have obtained its state of lowest mechanical potential energy. Of course, this doesn't happen, but why doesn't it? It's the consequence of the intermolecular forces that were first mentioned in lesson 10 on viscosity. Although some of these forces are sometimes pulling and sometimes pushing molecules around, overall, there's a net electromagnetic attraction occurring between adjacent molecules in most liquids. This attraction pulls the liquid together until an equilibrium is reached with other forces, in this case gravity. Surface tension is a measure of the contractive tendency that allows liquids to resist deformation by external force. For example, if we take this puddle and we very carefully place a paperclip on top of it, the paperclip imparts a force created by its weight on the surface of the water. This force pushes down on the surface, and this deformation of the water surface pushes apart the water molecules underneath the paperclip ever so slightly. If the sum of all of the attractive forces between the disrupted molecules is greater than the paperclip's weight, the clip will rest on the surface of the water. This is not a consequence of buoyancy, but rather of surface tension. Of course, our experience tells us that this only works for objects which are very light. In addition, surface tension is dependent upon properties of the liquid, the solid or liquid with which it interfaces, and the temperature. To understand how surface tension relates to physiology, it's important to describe something called the law of Laplace. Imagine a hollow sphere made of some form of pliant material, like plastic, for example, and inside is a thin layer of water coating the inner surface. The scale of this thin layer is greatly exaggerated in this picture, but the layer of water is made up of individual water molecules, all of which are attracting each other. The net sum of the circumferential attraction is that the water is actually being pulled inward. If there was no enclosed gas, the water would contract down into a ball. However, if there is enclosed gas, the result is an increase in the pressure of that gas. The surface tension pulls the water inward until an equilibrium is reached with the pressure pushing outward. The law of Laplace relates the surface tension to the enclosed pressure. It states that the pressure inside the spherical bubble is equal to 2 times the tension divided by the radius. Let's take a look in the lungs to see how this is significant. If we zoom way in, we will see that the 2 lungs are actually composed of roughly 1 billion sacs of air called alveoli, which are connected via an intricate branching network of air passages. Most of the details of this are not relevant for this discussion, other than to say that the alveoli are the site in the lungs where gas exchange occurs, and it's critically important that they stay open and don't collapse, or else oxygen will not be able to make its way into the bloodstream. So how is the law of Laplace applicable here? First, the lungs are a very moist place, and the insides of the alveoli are coated with water. Some alveoli may start off larger than others. Since the surface tension of water is independent of the size of the alveoli, based on the law of Laplace, a large radius results in a relatively low pressure, while a small radius results in a relatively high pressure. So when the patient takes a breath of air in, the air travels preferentially to the large alveolus with low pressure. Not only that, air could even travel backwards from the small alveolus with high pressure. The consequence of this is that large alveoli risk becoming overdistended and small alveoli risk collapsing altogether, a condition known as atelectasis. Alveoli that have totally collapsed can no longer take part in gas exchange, leading to diminished ability of the body to take in oxygen. This is obviously not good, so the body must have a way to prevent this from happening. It does, and it involves something called surfactant. A surfactant is a compound which reduces surface tension when added to a liquid. Most surfactants are amphiphilic, sometimes called amphipathic, which means they contain both a hydrophobic and a hydrophilic group. Here's the structure of a surfactant called sodium dodecylbenzene sulfonate, which is a common component of laundry detergent. Here's the hydrophilic group and the hydrophobic group. What effect does adding surfactant have to water? We saw earlier that water has a tendency to form puddles due to its intrinsic surface tension. These puddles are relatively thick, depending on the surface it lies on, and that is because its surface tension is relatively high. If we take an identical puddle of water and to it add some laundry detergent, the surfactants within decrease the surface tension, the effect of which here will be to spread the puddle out further. Let's look at another situation. We'll bring back Fido's dog bowl, and you can see that when it's filled with pure water, a carefully laid paper clip can float on top. For comparison, here's the dog bowl of his friend Spot, to which I'll also add some water. Now we certainly don't want to poison Spot with laundry detergent, so instead of detergent, we can give a different surfactant. An interesting one to use is dialkyl sodium sulfosuccinate, better known as docusate, or by the brand name of Colace. It's usually used as a stool softener, where its surfactant properties lead to increased incorporation of water into stool, making the stool softer and easier to pass. If we add docusate, which happens to be red, to the water, the surface tension decreases. Now a paperclip carefully placed on top won't float, and instead it will sink to the bottom. Let me return to the lungs to talk about pulmonary surfactant, which is a complex lipoprotein formed by cells called type 2 pneumocytes, which line the alveoli. The most notable constituent of surfactant is called DPPC, or more formally, dipalmitoyl phosphatidylcholine. This compound greatly reduces surface tension of the fluid coating the inside of the alveoli. Interestingly, unlike water, the surface tension of the mix of water and pulmonary surfactant is roughly proportional to the surface area over which it is spread. In other words, the power of surfactant to lower surface tension is most pronounced when the alveoli are smaller than when they are distended. Here are our two alveoli again, but the smaller one no longer has a relatively high internal pressure compared to the larger one. Instead, surfactant lowers the surface tension in the large alveolus by a modest amount, while it lowers the surface tension in the small alveolus by quite a bit. The fact that the surface tension in the small alveolus is particularly low offsets the effect of the smaller radius. As a consequence, the resulting internal pressure is low within both alveoli. So when air comes into the airways, both alveoli are inflated, improving gas exchange. So what are the net consequences of pulmonary surfactant? First, a reduction in the collapse of underinflated alveoli, otherwise known as atelectasis. Second, a more even distribution of ventilation amongst the alveoli, improving oxygenation. Third, it improves lung compliance. For the most part, a discussion of lung compliance falls outside the scope of this video. However, very briefly, Lung compliance is a measure of how much the volume of the lungs change in response to a change in pressure. The lower the compliance, the greater the pressure difference that must be generated in order to exchange the same volume of air. A major contributing factor to lung compliance is the alveolar surface tension, which has a cumulative tendency to pull the lung in on itself and resist inflation. Therefore, surfactant increases lung compliance, reducing the amount of work a patient or ventilator must do during inhalation. The last major clinically relevant aspect of surfactant has to do with preterm births. In humans, surfactant is not reliably produced until about 34 weeks gestation. Therefore, premature infants born prior to this may have significant difficulty with oxygenation and ventilation, a condition called infant respiratory distress syndrome, not to be confused with adult respiratory distress syndrome, which is quite different. Treatment of infant respiratory distress syndrome consists of a combination of positive pressure ventilation and exogenous surfactant delivered to the alveoli via instillation into the airways while intubated. If a mother is suspected to be at high risk of preterm delivery, she can be given antenatal corticosteroids, which speeds up the infant's synthesis and release of surfactant. So that concludes this video on surface tension. It also concludes this 12-video series on fluid mechanics in medicine. I hope you found these videos interesting and useful. Please remember to like and share those which you enjoyed, and feel free to ask questions as video comments.